South Florida sits on a bed of rock that was never meant to hold a city. The Miami limestone, the foundation beneath virtually every structure in the region, is riddled with holes. Dissolved over millennia by slightly acidic rainwater, the stone is so porous that engineers have compared it to natural Swiss cheese. In most coastal cities, bedrock acts as a barrier, a wall between the ocean and the built environment. In Miami, the bedrock is the problem. Water moves through it almost as freely as it moves through open air. Beneath that stone lies the Biscayne Aquifer, a superficial freshwater lens that stretches across more than 4,000 square miles and 3 counties. It is the sole drinking water source for millions of people, and it sits extraordinarily close to the surface. In most of the region, the water table hovers between 2 and 8 feet below ground level. That number is not a drought year anomaly or a seasonal low. It is the permanent condition of the land. The shallow depth of the aquifer means that anything built on top of it, roads, septic systems, building foundations, utility conduits, exists in constant negotiation with water that is, in many places, already pushing upward. This is the first thing that separates Miami's flooding problem from that of any other American city. The threat does not begin at the coastline. It begins underground. The Atlantic Ocean presses against the eastern edge of this porous limestone shelf with a force that increases as sea levels climb. Salt water is denser than fresh water, and as the ocean rises, it exerts hydrostatic pressure on the lighter fresh water sitting in the aquifer. The result is not a dramatic surge or a visible wave. It is a slow, invisible displacement. Fresh water is pushed upward, and salt water migrates inland through the rock itself, following pathways no seawall can block. The visible evidence of this process has become difficult to ignore. Since 1998, the frequency of sunny day flooding in South Florida has increased by 400%. These are not storm events. There is no rain, no wind, no named system on a weather map. Water simply appears, gurgling up through storm drains, seeping through cracks in pavement, pooling in intersections and parking garages on otherwise clear afternoons. The ocean is not coming over the wall. It is coming up through the floor. For more than a century, South Florida managed its water through a system designed around a single principle: gravity. A grid of roughly 1,800 miles of canals, levees, and floodgates was built to move excess water off the land and out to sea. The system worked because the land sat higher than the ocean. Engineers could open a gate and water would flow downhill toward the coast under its own weight. That difference in elevation, the hydraulic head, was the engine that made the entire drainage network function. As sea levels have risen, that engine has begun to stall. The difference in height between the water in the canals and the water at the coastal discharge points has narrowed. During high tides, the ocean now sits level with or above the outfall points of many canals. When that happens, the gates cannot open. If they did, seawater would flow inland, turning the drainage system into a conduit for the very water it was built to remove. During rain events that coincide with high tide, stormwater has nowhere to go. It backs up in the canal, spills over roadways, and floods neighborhoods that were dry a generation ago. Not because the rain is worse, but because the exit has closed. This is the condition the region was already in when the weather pattern designated Invest 90L formed in the Gulf of Mexico in June of 2024. Between June 11th and June 14th, a disorganized tropical system that never reached hurricane strength parked itself over South Florida and unloaded what forecasters later classified as a once-in-200-years rainfall event. At its most intense, rain fell at rates reaching 4 inches per hour. At Big Cypress National Preserve, west of the urban core, gauges recorded a peak total of 27.95 inches over the course of the event. Roadways flooded. Airport access roads went under. The system had no name and no eye, but it delivered more water in 3 days than the region's infrastructure was ever built to process. The timing made everything worse. With tidal levels already elevated, the canal system could not discharge fast enough. Water stacked up from the interior, met resistance at the coast, and spread laterally across low-lying neighborhoods. The rain did not create the failure. It exposed a vulnerability that had been building for decades, a drainage network that depends on gravity in a place where gravity is losing its advantage. In November of 2017, voters in the city of Miami approved the Miami Forever Bond, a $400 million general obligation bond designed to address the city's growing exposure to sea level rise and flooding. Of that total, $192 million was earmarked specifically for resilience projects, upgraded drainage, pump stations, seawalls, and infrastructure hardening. The bond passed with broad support. It was framed as a down payment on the city's future, a signal that Miami understood the scale of what was coming and was prepared to act. Nearly 8 years later, the money has largely sat unspent. As of late 2025, only 16% of the resilience portion had been spent or formally committed to active projects. The rest remained caught in layers of administrative process, permitting delays, design reviews, contractor procurement cycles, and interdepartmental coordination that move slower than the water. The cost of that delay extended beyond the bond itself. State and federal agencies had offered matching grants tied to the bond-funded projects, grants with expiration dates. As city-side timelines slipped, some of those matching funds expired or were redirected elsewhere. Money that was meant to multiply the bond's impact simply disappeared from the table, not because it was denied, but because it was never claimed in time. Meanwhile, across Biscayne Bay, Miami Beach was building its own defense. The city committed between $400 million and $650 million to an anti-flood program centered on a network of up to 80 pump stations. The pumps were designed to do what gravity could no longer accomplish: mechanically lift storm water off the streets and push it out to sea. It was an engineered workaround for a natural system that had stopped working. The pumps were sized to handle heavy rain, but the June 2024 event did not deliver heavy rain. It delivered rain at rates reaching 7 inches per hour in some locations, roughly twice the system's design capacity. Water rose faster than the pumps could move it. Streets flooded, basements filled. The system did not fail because it was broken. It failed because the weather exceeded the scenario it was built for, and in a warming climate, that scenario is no longer the ceiling. One station in Sunset Harbor lost power for 45 minutes during the event. For 3/4 of an hour, the pump sat idle while water climbed. When power returned, the system resumed, but the interval had already allowed flooding to reach depths that would not have occurred under continuous operation. The episode exposed a dependency that mechanical systems cannot fully escape. They require electricity, and electricity requires infrastructure that is itself vulnerable to the same storms the pumps are meant to fight. Below the streets, another system was failing on a different timeline. Miami-Dade County is home to roughly 120,000 septic tanks, many of them installed decades ago in neighborhoods that were never connected to centralized sewer lines. A septic system works by allowing wastewater to percolate through a drain field, a layer of soil and gravel that filters and absorbs liquid waste before it reaches the water table. The process depends on a vertical buffer of dry ground between the drain field and the aquifer. As the water table rises, that buffer shrinks. In many areas, it has already disappeared. Drain fields that once sat well above groundwater are now partially or fully submerged, which means wastewater is no longer being filtered. It is mixing directly with the aquifer, carrying bacteria, nitrogen, and pharmaceutical residue into the same freshwater supply that feeds drinking wells and canals. The contamination is invisible at the surface. It shows up in water quality tests, in elevated nutrient levels in Biscayne Bay, and in the slow degradation of nearshore marine ecosystems. The problem is not limited to septic systems. On January 12, 2024, Sewer Pump Station 28, known as PS28, suffered a mechanical malfunction that forced a temporary moratorium on new development in the surrounding area. The station, part of the county's centralized sewer network, was unable to process flows at the required rate, and the failure raised questions about the capacity and condition of aging sewer infrastructure across the region. Replacing the county's septic systems with centralized sewer connections carries an estimated price tag of $3.3 billion. That figure covers engineering, permitting, construction, and the physical disruption of retrofitting underground pipes through built-out residential neighborhoods, a process measured in years, not months. The financial exposure does not stop at infrastructure. By 2070, climate-adjusted risk models project that Miami-Dade County will hold $3.513 trillion in assets exposed to sea level rise, storm surge, and chronic flooding. That figure includes residential property, commercial real estate, transportation networks, utility systems, and public facilities. It represents not just what could be damaged, but what could lose value long before a single drop of water touches it, through insurance withdrawal, mortgage repricing, and market reassessment of long-term viability. The early signs of that repricing are already visible. A pattern sometimes called climate gentrification has begun to emerge, in which property values on higher inland ridges, once considered less desirable, are climbing, while waterfront properties in low-lying areas are softening. The market is not responding to a single flood or a single report. It is responding to a slow accumulation of signals: higher insurance premiums, repeated nuisance flooding, visible infrastructure strain, that collectively suggest the ground itself is becoming less reliable. The federal response has focused on protection rather than relocation. The U.S. Army Corps of Engineers has proposed the Back Bay Plan, a $2.7 billion initiative targeting storm surge reduction in the Miami area. The plan includes the physical elevation of roughly 2,100 homes, raising structures above projected flood levels to reduce damage from future events. It is one of the largest residential elevation proposals in American history, and it addresses only a fraction of the structures at risk. At the other end of the response spectrum, a $180 million pilot program has been proposed to test nature-based solutions: mangrove restoration, reef rehabilitation, and living shoreline construction designed to absorb wave energy and reduce inland flooding. These are slower, less visible interventions. They do not produce the same kind of before and after imagery that a seawall or a pump station does, but they operate on a different principle, working with the water rather than against it, and doing so at a cost that is orders of magnitude lower than hardened infrastructure. The question underneath all of these efforts is whether they are solving the problem or delaying it. Scientific projections for South Florida range from 3 to 7 feet of additional sea level rise by the end of this century. At the lower end of that range, much of the current infrastructure can be adapted, upgraded, or replaced. At the upper end, large portions of the built environment sit below the projected waterline, not during a storm, but permanently. That gap between 3 feet and 7 feet is where the debate over managed retreat begins. It is a phrase that appears more frequently in planning documents and academic literature, though it remains politically charged and practically undefined. What it means, stripped to its essentials, is the organized preemptive relocation of people and infrastructure away from areas that can no longer be defended against water at a reasonable cost. No major American city has attempted it at scale. The engineering is not the obstacle. The obstacle is everything else: property rights, community identity, economic disruption, and the fundamental difficulty of asking people to leave a place that is not yet underwater, but maybe within their lifetime. South Florida's problem is not that a storm came. Storms have always come. The problem is that the land itself is changing, slowly from below, in ways that no single bond or pump or seawall can fully reverse. The water is not arriving. It is already here, moving through limestone, pressing upward through the aquifer, sitting just beneath the surface, waiting for the next high tide or the next heavy rain to make itself visible again.